Welcome to our deep dive into the world of GANs.
Generative Adversarial Networks.
I got it.
You're clearly into AI. So
Oh, yeah.
we're going to unpack the paper that really revolutionized the field.
Okay.
Generative Adversarial Nets, published way back in 2014
Wow.
by Ian Goodfellow and his team.
So this is really where it all began.
This paper's where it all began.
Before this.
Before this, creating realistic synthetic data was a real challenge.
Right.
But this paper introduced a whole new framework, a whole new way of thinking about how we train machines to create.
So let's break down this framework.
Okay.
At the heart of a GAN, we have two neural networks,
Right.
the generator and the discriminator.
Yeah.
And they're not just working together,
They're not just working together.
they're engaged in a kind of competition.
It's a fascinating dynamic.
Yeah.
The generator is like a team of artists trying to create masterpieces,
Oh, okay.
while the discriminator acts as the art critic, trying to determine if a piece is genuine or a clever forgery.
I love that analogy.
Yeah.
And just like in the art world, this constant back and forth.
It pushes both sides to improve.
Right.
The generator gets better at creating realistic data, while the discriminator becomes more discerning, more adept at spotting the fakes.
Precisely.
The paper itself uses a similar analogy.
Okay.
The counterfeiter and the police.
Oh, interesting.
The generator, our counterfeiter, takes random noise as input.
Okay.
Think of it as a blank canvas or a jumbled set of notes.
Right.
Its task is to transform this noise into something resembling the real data. It's trying to mimic images, music, even text.
And the discriminator, the police,
Yes.
is constantly trying to catch them out.
Exactly.
It's trained on a data set of real data
Right.
alongside the generator's output,
Alongside it, yep.
learning to distinguish between the genuine article and the counterfeit.
It's like a never-ending game of cat and mouse,
Oh, wow.
with both networks constantly learning and adapting.
Oh. And what's amazing is that the paper provides a mathematical proof demonstrating that, in theory,
In theory.
a perfectly trained GAN can perfectly replicate the data it's trained on.
That's right.
Now that sounds a perfect replica. What does that actually mean?
Yeah.
And why is it so groundbreaking?
Imagine being able to generate synthetic data for medical research.
Okay.
That is statistically identical to real patient data,
Wow.
but without any of the privacy concerns.
That's huge.
Or imagine creating virtual environments for training self-driving cars
Okay.
that perfectly mirror real-world conditions.
Oh, wow.
That's the power of replicating data distributions.
So both the generator and the discriminator
Yeah,
are typically multi-layer perceptrons.
right.
You might be familiar with other types of neural networks.
Sure.
This is just a particular architecture.
It's a particular architecture that's proven very effective in lots of machine learning tasks.
And these two networks are locked in a constant struggle,
Yes.
mathematically represented as a minimax game. The generator aims to minimize the discriminator's ability to detect fakes,
Right.
while the discriminator tries to maximize its accuracy in spotting them.
It's a constant back and forth.
Sounds like a pretty intense game. How do we even know who's winning?
Well, the training process
Yeah.
is guided by what's called a value function,
Okay.
which quantifies this adversarial dynamic.
Okay.
Both networks are constantly trying to optimize this function, pushing each other to improve.
So they're always getting better.
Always getting better.
But it's a delicate balancing act.
It is.
So what happens if this balance is thrown off?
Right.
What if one network starts to dominate the game?
That's where things can get a bit tricky.
Okay.
Let's say the generator becomes too good too quickly.
Yeah.
It might start producing very similar outputs, lacking diversity.
So not very creative.
Not very creative, no.
Okay.
Imagine a world where all cats in pictures generated by AI looked exactly the same,
Right.
even though real cats come in all shapes and sizes and colors.
Of course, yeah.
This is sometimes referred to as the Helvetica scenario.
Helvetica.
Like a world where every font looks like Helvetica.
So it's not enough for the generator to just create convincing fakes.
It's not enough, no.
It needs to capture the full richness
The full richness.
and variety of the data distribution.
Exactly.
It's like a chef who can perfectly replicate a famous dish,
Yeah.
but can't create anything original.
Exactly.
Right.
And this is just one of the challenges researchers face when training GANs.
Yeah.
It's a fascinating field full of complex dynamics and exciting possibilities.
Absolutely.
Yeah.
Okay. So we've talked about this analogy of the counterfeiter and the police.
Right.
But what's actually happening under the hood? What's the math?
Yeah, the math behind this creative competition.
Right.
At its core, The generator is trying to learn
Okay.
the probability distribution of the real data.
The probability distribution.
Yeah, it's trying to figure out
Okay.
the underlying patterns and variations that make the data what it is.
So if it's learning to create images of cats,
Yeah.
it's not just learning what a cat looks like.
It's not just learning what a cat looks like.
It's learning how likely it is for a cat to have
Exactly.
certain fur patterns,
Certain fur patterns.
ear shapes, eye colors.
Yeah, all the subtle variations that make each cat unique.
Right.
It's like learning the recipe for catness,
Okay.
not just copying a single picture.
Got it.
And the discriminator's job
Yeah.
is to estimate the probability that a given image came from the real data set
Okay.
or the generator's output.
So it's like a detective
It's like a detective.
trying to determine the authenticity
The authenticity
of a piece of evidence.
a piece of evidence, exactly.
Okay. So both networks are working with probabilities.
They are.
But how do we actually measure
Yeah. How do you measure?
how well the generator is doing in this probability game?
Well, the paper introduces this concept of the optimal discriminator.
Optimal discriminator.
Yeah.
Like it.
Imagine a scenario where, for a given generator,
Mm-hmm.
there's a discriminator that's perfectly trained
Right.
to distinguish real cats from generated cats.
Okay.
That's our optimal discriminator.
So the best possible detective.
The best possible detective for that particular counterfeiter.
Okay. Got it.
And here's the key insight.
All right.
When the generator perfectly replicates the real data distribution,
Mm-hmm.
even this optimal discriminator
Mm-hmm.
can only achieve 50% accuracy.
That makes sense if the generated cats are indistinguishable from the real cats.
Exactly.
Even the best cat detective would just be making random guesses.
Just be making random guesses.
Right.
And this 50% accuracy mark
Okay.
becomes a critical point in the training process.
Yeah.
It tells us that the generator has achieved its goal.
It's learn the secret recipe for catness.
It's learned the recipe.
So the training process is all about guiding the generator towards this point,
That's the essence of it.
where it can fool even the best possible discriminator.
Yeah, and the paper takes this idea even further, proving mathematically that this equilibrium point, where the generator replicates the data distribution perfectly,
Right.
is the global minimum
Okay.
of what's called the GAN's objective function.
Okay, let's break that down a bit.
Sure.
What is an objective function?
Yeah, what is an objective function?
And why is this global minimum so important?
Think of the objective function as a mathematical formula
Okay.
that quantifies the difference
Uh-huh.
between the generator's output and the real data.
So how far off it is?
How far off it is, yeah.
Okay.
The lower the value of this function,
Yeah.
the closer the generator is to achieving its goal.
So the global minimum is like the lowest point on a map,
That's a great way to visualize it.
like the ultimate destination for the generator.
The ultimate destination, and the paper uses a concept called the Jensen-Shannon divergence
Jensen-Shannon divergence.
to measure this difference between distributions.
Okay.
Imagine you have 2 bags of candy,
Okay, 2 bags of candy.
one representing real data and the other generated data.
Okay.
This divergence measures how different the mix of candies is in each bag.
So the goal is to make this 2 bags of candy as similar as possible.
Exactly. And the mathematical proof shows
Okay.
that the lowest possible divergence, meaning the most similar bags of candy,
Yeah.
occurs when the generator perfectly replicates the real data distribution.
This all sounds very elegant in theory,
It does.
but how does this mathematical proof actually translate
Yeah, how does it translate?
into the training process? How do we get the generator to reach this global minimum?
The training process can be seen as a gradual descent
Okay.
towards this minimum.
Uh-huh.
Both the generator and the discriminator are constantly being updated.
So they're constantly learning.
They're constantly learning, like
Okay.
2 hikers adjusting their course as they navigate down a mountain
Right, towards the lowest point.
towards the lowest point. Exactly.
But we need to make sure they're both descending at roughly the same pace, right? We talked earlier about the Helvetica scenario,
Yeah.
where the generator might get stuck,
Yeah, it could get stuck.
producing very similar output.
Very similar output.
If it progresses too quickly.
If it progresses too quickly, Zach,
So it's like making sure the
the
detective
detective
doesn't get too far ahead of the counterfeiter.
doesn't get too far ahead.
We need to keep them both engaged in the game.
Absolutely. The paper outlines
Okay.
a specific algorithm for training GANs
Right.
that aims to prevent the discriminator from getting too good too fast,
From becoming too powerful.
too powerful.
Okay.
If the discriminator becomes too powerful,
Yeah.
the generator might struggle to catch up,
Right.
and the training process can become unstable.
So instead of both networks kind of converging towards the optimal solution,
Right.
they might end up chasing each other in circles
They might end up chasing each other,
and never reaching their full potential.
never reaching their full potential.
Wow, okay.
And another common issue
Yeah.
is a more severe form
Okay.
of the Helvetica scenario
Uh-huh.
called mode collapse.
Mode collapse.
Imagine our counterfeiter gets stuck producing only $10 bills,
Okay.
even though there are other denominations in circulation.
So instead of capturing the full diversity of the data,
Full diversity.
the generator just fixates on a small subset,
A small subset.
leading to repetitive and less realistic outputs.
Exactly. Mode collapse can be a major obstacle
Yeah.
in GAN training, and researchers are constantly developing new techniques to address it.
So we've spent the last two parts really getting into the nuts and bolts of GANs.
The theory, the math, the
Yeah.
training process.
But let's step back now and look at the bigger picture.
Okay.
What impact are GANs actually having out in the real world?
The impact is already huge, and it's growing rapidly
Wow.
across many fields. Let's start with something we can all visualize: images.
Okay.
GANs are completely changing the way we edit and create images.
Yeah, we've all seen those apps that can age your face or swap faces in photos, or even create photorealistic images from scratch.
From scratch.
Yeah. It's pretty mind-blowing.
And these aren't just fun gimmicks.
No.
Professionals in photography and film
Right.
are using GANs to create special effects
Uh-huh.
and enhance image quality
Yeah.
in ways that were simply impossible
It's
before.
like having a whole team of digital artists at your disposal,
It is.
ready to create anything you can imagine.
And beyond images, GANs are making waves in audio and music production.
Really?
They can generate incredibly realistic sound effects,
Wow.
synthesize new musical instruments, even compose entire pieces of music in different styles.
So are those AI-generated songs we've been hearing about actually using GANs?
In many cases, yes.
Wow.
And it's not just about creating brand new sounds.
No.
GANs are being used to restore old recordings,
Okay.
remove noise from audio,
Uh-huh.
and even personalize music experiences for individual listeners.
It's like giving musicians and producers
It's like giving
a
a
whole new set of tools to explore and create with.
whole new set of tools, yeah.
But it seems like GANs are reaching far beyond just the creative fields.
Absolutely. GANs are proving incredibly valuable in medicine and scientific research as well.
Now we're talking about real-world impact.
Real-world impact, yeah.
How are GANs being applied in those areas?
In medicine, GANs are helping to generate synthetic medical data,
Okay.
which is crucial for training AI models while protecting patient privacy,
Right. So instead of relying solely on real patient data,
which can raise ethical concerns.
of course.
Researchers can use GANs to create realistic, anonymized datasets for
Okay.
training algorithms.
So GANs can actually help accelerate medical research
They can.
while maintaining patient confidentiality.
Yes.
That's amazing.
They can also be used to enhance medical images,
Okay.
making it easier for doctors to diagnose diseases.
So like giving doctors a better look
A better look.
at what's going on.
Imagine a world where GANs can help radiologists spot tumors more accurately, or assist cardiologists in analyzing heart scans.
It's like having an extra set of highly trained eyes,
An extra set of eyes.
working alongside medical professionals.
Working alongside them.
What about the impact on scientific research?
GANs are being used to simulate complex phenomena across a wide range of scientific disciplines,
Okay.
from astrophysics to climate modeling.
Wow.
They can generate vast amounts of synthetic data
Uh-huh.
that would be impossible or prohibitively expensive to collect in the real world.
So it's like giving scientists a virtual laboratory
A virtual laboratory.
where they can test their theories and run experiments
Yeah.
at a scale that was never possible before.
Exactly.
That's incredibly powerful.
And these are just a few examples of how GANs are transforming various fields
Yeah.
as research continues
Mm-hmm.
and the technology matures. We can only expect even more innovative and impactful applications to emerge.
This has been an incredible journey exploring the world of GANs from the foundational concepts
It has been.
to the real-world impact they're already having.
It's a testament to human ingenuity and the incredible potential of AI to transform our world in positive ways.
We began this deep dive by asking, what's the big deal about GANs?
Right.
And I think we've clearly answered that question.
I think so too.
They're not just a technological marvel.
They're not.
They represent a fundamental shift in how we think about creating and understanding data.
And it's clear that this is just the beginning.
Yeah.
The future of GANs is full of exciting possibilities.
To our listeners, thank you for joining us on this deep dive.
Thanks for listening.
We hope you've gained a deeper understanding of the power and potential of generative adversarial networks.
We hope you enjoyed it.
Keep exploring, keep learning, and keep diving deep.